Hello, everyone. Welcome to the Casual Causal Podcast, episode 12. Today, we have with us one of the most leading time series forecasting experts in the world, Dr. Stephan Kolassa. When it comes to time series, we humans have been documenting time since the dawn of ages, and we have also been making a lot of forecasting based on it. Dr. Stephan, it's a pleasure to have you here. How are you doing today?
Wonderful, Venkat. Thank you so much for having me on here. I'm so much looking forward to this discussion here.
Yeah, I must say that, before the advent of ChatGPT and Perplexity, your answers on cross-validated were the go-to solutions for many of us, including me. So thanks for all your answers on, cross-validated over the years.
Oh, so I'm glad to know that I've been of help to you and hopefully to others from what I hear. And I sure hope that people will still come to cross-validated even after traffic, of course, has been dropping precipitously. Because, of course, most people will now ask their LLM of choice for statistical and forecasting and time series expertise. And unfortunately, sometimes this expertise, this knowledge that LLMs give you is not the very best you can get, because honestly, LLMs have been training on the entirety of the internet, and there is a lot of misinformation and misunderstandings on all of statistics out there. And LLMs have been training on that, and they're happily and faithfully regurgitating all these misunderstandings back at you. And so I think that many people would be well served to come to cross-validated and actually learn from a host of extremely good people that are on there and that have already built a repository of about 200,000 questions and answers. And some of these are real gems. And I'm not only talking about forecasting, but anything that has to do with data science, statistics, and so on. So I hope people will still come there.
Absolutely agree. There was some report that, most of the LLMs is trained on Reddit. What if they were trained on authentic resources on cross-validated? Things would have been much different. But yeah, that's a wishful thought. But we hope that, going forward in the future, all these LLMs go to, very renowned resources like yours to, get answers from. But yeah, starting with today's question, Stephan, tell us about your career journey. How did you get started with forecasting, statistics, and ML?
Actually, I'm not a forecaster by training. I'm by birth, I'm a mathematician, so I studied mathematics. But while I studied, there was this young lady who was a psychologist, and every psychologist needs a statistician to analyze their data. And the place where we studied, there was no school of statistics, so she did the next best thing and grabbed a mathematician and remodeled him into a part-time statistician. And a couple of papers later, I married her. And when we finished our PhD and I was looking around for a job, I applied for a job at this forecasting company, this small startup. And one of the founders was a professor of economic statistics. And he looked at my CV and said, well, this guy has 5 publications in inferential statistics for psychology. This guy can do forecasting. So they hired me. And then, I had to do forecasting for retail, and that was completely new to me. And so I looked around for resources. That was 20 years ago, so much less out there than today, a couple of textbooks, and that was all. And I found out about this International Institute of Forecasters that were doing an annual conference, International Symposium of Forecasting. And then I attended that back in 2006, I think, the first time in lovely Spain. And that kind of sucked me into this vortex of these forecasters out there, and the rest is, I would say the rest is history, but of course for forecasters, history is what you train on, so probably better to say the rest is forecasting. And so I still have this one foot in this inferential statistics camp with my wife, who's by now a full professor of psychology, clinical and biological psychology. So I regularly talk to her about her analyses, and that's a completely different field from forecasting. It's purely inferential statistics. So my approach to forecasting is really heavily tinged by this inferential background that I have, and the other way around. When I talk to her, often have suggestions that a typical inferential statistician would not have for her. So I'm kind of sitting between all chairs, but that's a comfortable place to be because it's interesting.
Very interesting story. time series is omnipresent, and you can see that, we are also literally named after the time series forecasting technique ARIMA, but we have a Y hat in between because we are estimating things. When we talk about, time series forecasting, be it stock prices, be it heartbeats, even LLMs to a certain extent, time series seems to be everywhere. Why do you think it is such a natural format for the world around us?
Well, that's a good question, and I would probably have to ask a philosopher about that, somebody who's doing metaphysics, because it's just a fact of life that we're living on a time arrow, right? Time moves forward, and everything that we do is time ordered, and that's just a completely natural way of looking at things. And there's time dynamics everywhere. And I would honestly, I'd rather turn the question around: what is there that is not a time series or time dependent? Because if you look into machine learning or data science or whatever, first things that you learn about are stuff like credit scoring. And if you do credit scoring with somebody, then of course you need to keep in mind that there is a history going back, and that were booms and busts, and people perhaps they lost their jobs at some point in time, and your credit scoring will use that to assess their credit worthiness. But of course, losing a job has a lot to do with the economic situation at that point in time. So you really need to keep in mind, okay, did this person lose their job during a downturn where it may not have been anything to do with them, or did they lose a job at a time when the economy was booming? And then it's perhaps a bit more of a red flag. And so you always need to keep in mind this flow of time. Or another example, looking at image classification. So another thing that people have been doing nowadays, the image classifiers are so good that I think, interest is waning in that. But people used to classify images, pictures. Is this a cat or a dog or something? Just imagine you'd be training your classifiers on ancient Egyptian illustrations of cats and dogs, or on medieval illuminated manuscripts of cats and dogs, and those would not be very helpful in classifying today's pictures, photographs of cats and dogs, simply because there's a distribution shift involved here. We just don't see it because we have enough data that's in the current distribution that are current electronic pictures of cats and dogs. And so we're not seeing that time dependency that we have in here, and we can disregard it and we're still good. But in other cases, you really have to keep that time dependency in mind, and not just say, okay, well, let's treat every point in time as independent or exchangeable or something else.
Great explanation. Now that we have explained what is time series, would you like to explain to our audience what is time series forecasting?
Okay, well, time series forecasting is, well, you have a time series, you have some observations ordered in time, typically a history of observations, and you want to forecast the future. So the next points in time, the observations that come in the future. And as I said, all predictive applications are typically in this setup. It's just that sometimes you keep this time information because it gives you a lot of information, a lot of structure, and sometimes you remove it. If you're classifying pictures of skin as to whether this might be cancer, skin cancer or not, you typically don't need this time dimension unless you're looking at a time series of pictures of one person. But typically, if you're just training your neural network, you disregard that. But in other cases, the time ordering is absolutely crucial. And yeah, as I said, my main focus is on retail forecasting. So not going to go deep into details on that. Actually, I have YouTube videos on that if anybody's interested, but that will always inform the examples that I bring here. So in retail forecasting, you have a supermarket and you need to forecast tomorrow's sales for a given product. So the supermarket can replenish ahead of time. And if tomorrow a promotion starts, then this is hugely important. And even if there is no promotion, then yesterday's sales or last week's sales or the sales 1 year back bring a huge amount of information that can help you forecast much better and yield a better stock situation in the end. If you have seasonality, if you have life cycles and so on, all these are time dependent information that you simply cannot disregard. You cannot just say, okay, let's treat this day as everything else, because, well, fall is starting in the northern hemisphere, spring is starting in the southern hemisphere, and that is just completely different from winter and summer for certain assortments. So you need to keep that in mind.
Mm-hmm. Once we have delved into, what is time series forecasting, then the question of, what are the components of time series comes up. Would you like to explain what are the components of a time series forecasting and how are they decomposed?
Okay, once again, a topic that you could spend 2 hours on all by themselves. So let's try and keep it short, and you'll
Yeah.
interrupt me when I talk too much. There is no hard and fast definition of components of a time series. There is a very standard technique called STL, season and trend decomposition using LOES. So LOES is a local smoother essentially. So you have a time series, and you want to figure it, and you want to decompose it typically additively into a season, so a recurring pattern. Think of the seasonal sales of ice cream higher in summer than in winter. So you have a season in there, day of year, for instance, or month of year. You have a trend component, typically not for ice cream because ice cream consumption is stable, but many other things have a trend, so upward or downward trend. And the remainder, everything else, everything that's boring. And that's one decomposition. And other decompositions are like in exponential smoothing that we might be talking about later on, where you decompose and separately forecast these levels, a level or these components, a level, an overall level of the time series, a trend component, and a season component. So in contrast to STL, here you have an explicit level component, which in STL really it gets absorbed into the trend component. And the advantage of these of looking at time series using components is always that if you can additively decompose stuff, then it's easier to understand the seasonality and the trend. You can just forecast each component separately and then recombine the forecasts again. And that is a very simple approach, and it's very easy to explain, especially for the non-specialist. And explainability is something that I've found over the years to be more important than many forecasters might think, because the non-forecasters need to understand what you're doing, or at least be comfortable and be confident that you know what you're doing. Otherwise, they'll not accept the forecast.
Interesting. Of course, we're going to talk about explainability later down the segment. You talked about Loess smoother, right? What is smoothing exactly? If you were to explain it to a layman, why is it even called so?
Okay, smoothing, and the prime example in forecasting is really exponential smoothing. Exponential smoothing is, yeah, as I said, prime example of smoothing. You typically you have a forecast for tomorrow's observations, whatever that might be, and perhaps you're forecasting 10, you actually observe 12. And now you want to update your forecast for the day after. So you just observed something that was a little higher than what you had forecast for tomorrow. And so you'll adjust your forecast up a little and you say, okay, let's pick something like 10.5. So you adjust a little into the direction of what you actually observed. So now your forecast becomes 10.5. If you again observe 12, then you adjust a little more, perhaps to 11 or something like that. And what that means is that since you're iteratively adjusting your forecast, once you do the math, it turns out that each observation has an impact on your forecast, and the observations have a weight that decays exponentially. So the most recent observations has the highest weights, and the most distant observations have the lowest weights. And that's this exponential decay in weights, that what they call it exponential smoothing. And it's smoothing because it smooths out the variability in the time series. So even if it juggles up and down, your forecast will not react extremely quickly to the time series, but be smoother than the time series itself. And that's essentially exponential smoothing, or simple exponential smoothing, because there's also variations on that, where you can also use a trend component and or a seasonal component. And then the philosophy is always the same. You have a forecast that is perhaps an addition of multiple components like level, season, trend. You have a new observation and you update your components, level, trend, seasonality, by taking the difference between the forecast and the actual observation and essentially distributing that among these different components. And so you smooth these components separately and forecast them out and then recombine them. And there's an entire zoo of exponential smoothing methods. You also can use something like multiplicative trends or multiplicative seasonalities. You can now use all kinds of errors. And that's a very established technique that I personally like very much because it's so simple. You can explain it to people, and it's actually surprisingly effective. I wonder, perhaps I'll just say it right now here. I just recall there was a forecasting competition. There's multiple forecasting competitions. So the Makridakis competitions, the M's, M1 through M6 by now. And perhaps we can should we start talking about the competitions, or should we do that in a separate question?
No, you can please carry on. No problem at all. Yeah.
As I said, I like talking because I like forecasting so much. So you might need to interrupt me at some point in time. So there's these Makridakis, or these M competitions that were initiated by Sibelius Makridakis, one of the great names in forecasting. And the first one was in 1982 or 81 or something, the M1 competition. And that already was very interesting because at that time, people were heavily using ARIMA. So in autoregressive integrated moving average. We might talk about that later on. And along comes Spyros Makridakis and did this forecasting competition. Then back then it was all pen and paper and people sending in their submissions via mail. So actual paper mail, not email. So 40 years ago, a long time ago. And it turned out that exponential smoothing outperformed ARIMA, and quite heavily so. And when they publicized their findings and submitted them to journals, and statisticians that were doing the forecasting method said that this can't be right, because we know that ARIMA is optimal for forecasting. If you have an ARIMA process, then ARIMA will give you optimal forecast. So if exponential smoothing, this method that didn't have at that point in time the statistical rigorous foundation, it was a very ad hoc method. And the simple formulations that I just gave is still very ad hoc. It doesn't have any statistical justification. If that outperforms ARIMA, then obviously Spyros Makridakis must have made an error in implementing ARIMA. They didn't quite put it like that, but the subtext was there. and that was interesting. But honestly, the proof of the pudding is in the eating, and the proof of the forecasting is in the forecast, and exponential smoothing simply outperformed ARIMA. I have my suspicions on that. And fast forward to the M5 competition. So there were M2, M3, then along hiatus, then M5 and M6, M4, M5, M6. The M5 competition that I wanted to talk about in this context of exponential smoothing, M5 used retail data from US retailer Walmart. They had 3,000 products and 10 stores, so they had about 30,000 time series and all kinds of hierarchical aggregations. We might want to talk about hierarchies later on too. So there were actually 12 different aggregations that entered into the evaluation of this forecasting competition. So people had to forecast everything. They had to forecast these bottom level series, these 30,000 series. They also had to forecast total sales per store or total sales per stock keeping unit across 10 stores, all kinds of things here. And there is one very interesting, tiny little sentence in the paper where Makridakis and collaborators discussed the results, and this tiny little thing was that 92.5% of submissions did not outperform a very simple exponential smoothing at the bottom level that was then bottom-up aggregated. 92.5% did not outperform that. And I found that fascinating because very probably lots of people just did their first model and did a little feature tuning and just uploaded the forecasts, and the leaderboard told them, no, sorry, exponential smoothing is better than what you just did. And they probably looked at that in shock and said, well, how can exponential smoothing, this very simple 80 years old technique, exponential smoothing goes back to the 1940s and 1950s, how can that outperform my lovingly tuned like GBM model here? I'm not going to worry with this anymore. There's something strange going on. I don't want to invest the time to outperform exponential smoothing. And that there is a lesson in here, right? The lesson is that you can get very, very good forecasts with exponential smoothing with very simple methods, and outperforming that actually takes a fair amount of work. And so there's one thing that I like to say in forecasting. Simple methods are often extremely and surprisingly hard to beat, but you wouldn't know if you just followed people on Kaggle and publications in academic journals and all kinds of tutorials. Because of course people, they don't have an interest in saying, okay, I have this lovely new forecasting technique, but unfortunately exponential smoothing is better than that. Stuff like that doesn't get published. Stuff like that doesn't get publicity. And so I'm sure that lots of people out there have been trying the most newfangled inventions only to find that a very simple method outperformed them. And they may just have gone with a simple method, but then they probably wouldn't publicize that because who wants to hear about that? Or there might be internal political incentives if you're a data scientist and you essentially say, well, exponential smoothing, which can simply be done in Excel, that outperforms anything that I can bring to the table. I don't know whether the data scientists will be comfortable telling that to their manager, and there may be political pressures for people to still adopt more complex methods and tie themselves into pretzels to motivate that they're using some kind of transformer-based approach. So, sorry, I like to talk, as you see. You may need to interrupt me once in a while.
No, not at all. Very interesting story, I must say. Just touching upon that story, was there ever a deep research conducted on why exponential smoothing almost always beat all these really fancy techniques like JBM, XGBoost, etc.?
Not that I really know of, and it's very hard to say that because it's my personal approach or understanding, my personal explanation for that effect is that very often the signal in the data is quite weak and the noise is quite high. And in situations like that, well, a complex method will have low bias and high variance. Yeah, but very often a high bias, low variance method like exponential smoothing can simply give you a smaller whole mean squared error or whatever it is. It's just a case of the bias variance trade-off. And that is a qualitative explanation, but it's very hard to really say, okay, how does this apply to a particular data set, a particular time series? And I'm absolutely not saying that exponential smoothing is the end all of forecasting. And there are certainly cases where it makes sense to use more complex methods. The thing that I'm arguing is that you should always keep these simple methods in mind as a benchmark and compare the more complex ones to that.
Yeah, very true. I was following, these M3 competitions, the M series competition, to put it rightly. And I was observing that, the winning team and the second team or the third team were just differing by a very few percentage points, like 0.2, 0.3 percentage points. It's very close, right? Something very similar to what happens in Kaggle also. The accuracy percentage is 99.2 and the winning team is having 99.23. It's almost like Formula One racing where you're looking at the the 100th second or the 1000th second, something like that, right?
Yeah, absolutely. And for instance, I think Robert Files and Xiaohui Ma in their commentary on the M5 competition pointed that out, that honestly, there are so many submissions, thousands of submissions, somebody has to win. And of course, there is some randomness involved in here. And while somebody has to win, I would not be very confident to say that the top contender will reliably outperform other contenders, even on other Walmart data, even on the same data. Even if you looked at Walmart and picked 10 other stores in the same time frame, or picked the same 10 stores, the same 3,000 SKUs, going forward beyond the competition horizon, I would not be confident that the current winner would be the one to outperform all others going forward, because there's just so much noise and so much randomness in here. Somebody has to win, right?
Yeah, true. We touched upon ARIMA a little bit. Let's say that it's one of the fundamental forecasting techniques. Is it the hello world equivalent of time series forecasting?
Well, actually, I think calling it the Hello World program of forecasting makes perfect sense because just as when you learn a new programming language or something, the first thing you do is make it type or print or whatever, Hello World. And that's just like you start, you make sure it's working, it's doing something. But of course, in a real situation, you would never be having it output hello world. And ARIMA is very similar. ARIMA is something you can apply to a forecast or to apply to a time series to get a forecast. And honestly, it isn't working very well. In time series forecasting, at least, ARIMA is usually not a top contender. It's a benchmark. It's very often outperformed by exponential smoothing. The problem is, even if it's not top contender, it's in all the textbooks, and it's what you learn first if you learn about forecasting. You go to forecasting on Wikipedia. I haven't looked at the page in the recent past, but I would assume that ARIMA is still on there. Forecasting, here's ARIMA, here's exponential smoothing. So of course, when you write a new textbook on forecasting or a new tutorial, you need to write about ARIMA because everybody knows ARIMA, and so it gets perpetuated.
Mm-hmm.
But honestly, ARIMA, well, it's and the advantage, of course, is that there are very good implementations of ARIMA. So there's Auto ARIMA in the forecast and fable packages for R. I still use R, I have to admit. There is the older PMD ARIMA, and nowadays the mixed implementations of Auto ARIMA for Python and everything else. Everybody has ARIMA, and there is a reasonably, and the current approach of selecting models by Akaikis information criterion and so on, that's very stable and gives quite satisfactory results, again, as a first baseline. Typically very often outperformed by exponential smoothing and doesn't deal with all kinds of forecasts, but it's a workhorse that you kind of need to know.
Great. We use R predominantly too at Aryma Labs. It simply works, and there are so many libraries and methods out there within R. But when it comes to productizing a particular product, we do leverage Python. But yeah, most of the R&D and the workhouse, if I may call it, is R for us because we deal with time series and market mix modeling. As you understand, is all about time series at the end of the day. Just building upon Aryma. Let's talk about the individual components of ARIMA, AR, the autoregressive component, then the integrated component, and then finally the moving average component. What purpose do each one of them serve?
Okay, let's start with the AR component because it comes first. The AR is autoregression. So essentially, you say you model tomorrow's observations as, for instance, 0.4 times yesterday's observations. That's an AR1 model, or today's as a function of tomorrow's as a function of today's. That's an AR1 model. If you model tomorrow's observations, so your forecast is 0.4 times today's observation minus 0.2 times yesterday's observations, that looks back 2 steps in the time series. That's an AR2 model. So on. You can do up to AR whatever you want. So that's the The I, let's keep that for a little later. Let's look at the MA moving average component. The moving average is essentially you have a forecast for today. That's always wrong because all forecasts are wrong. So you have an error. And what you do is then you forecast for tomorrow 0.2 times today's error, essentially. So you look back into the error, not in the actual value, but into what was the error compared to the forecast for today. And again, and that's an MA1 model, essentially. And you can look back to the error for yesterday's forecast and for today's forecast and use a weighted average of those, and that's an MA2 model. You can put them together. Then you have an ARMA model, an ARMA model, where you have a forecast that depends both on today's and yesterday's and day before yesterday's observations and the errors, the innovations, the residuals from all of these days. So you can have an ARMA 3.2 model that looks at the last 3 observations and the last 2 innovations or residuals. That's an ARMA model. Finally, let's look at the I. Sometimes you have stuff like trends or non-stationarities or whatever, and then you might want to not model the time series itself, but you take the time series and you take successive first differences. So you look at the observation for today minus the observation from yesterday. And you look at the observation yesterday minus the observation from the day before that. So what you're modeling is not the time series itself, but the change time point over time point. And that's, if you just take first differences, that's an I1 situation. And then you can model these first difference time series using an ARIMA model. Suddenly you have an ARIMA model with a, for instance, 3 AR components, 1 difference, and in the middle component would be 1, and perhaps 2 MA components, and then you have an ARIMA 312 model. And for the I, you can also take successive differences, so you take first differences and difference them again, then you have second differences, and that's actually models something like a quadratic trend, and you have an I2 model, and you have an ARIMA 322, or something like that. Now, of course, if you have a given time series, nobody's telling you what the correct ARIMA model is. And so you need to figure out, okay, which order do I have to put in there? The second step would then be, now I have an order, now I have to estimate the parameters for the AR and the MA component. So do I need to take 0.4 times today's observations or minus 0.3 times today's observations? This parameter needs to be estimated. You need a common filter or something like that. But to first figure out which order I need to look at, that's a very complicated problem. And there's still this old approach by Box and Jenkins that was propagated, I think, in the 1960s in their fundamental textbook, and people are still using that, or at least teaching that, where you look at autocorrelation functions and partial autocorrelation functions. And I always look at that, and I have one question on cross-validated about that. Has there ever been any research into how that should work? I mean, how do you scale that? How do you scale, look at an ACF plot and see whether it decays exponentially? Well, how do I decide that a given ACF plot that goes up and down, has lots of wiggly things in there, how do I decide whether that decays exponentially or whether that fluctuates and stuff like that? And when you look at these descriptions, there's so much hand waving going on in here. And nowadays, a more modern, more robust implementations coming from the forecast packages and then also integrated into the Python libraries. That would be first do a couple of unit root tests to determine the order of integration. Once you fix that, you look at the orders of the AR and MA components by just iterating, looping over the search space and doing a greedy search to minimize the Akaike information criteria. And that works very well. And that can be scaled and that can be implemented with no need for people to look at plots and parse them, which especially for the beginning user is extremely hard. That's ARIMA, and that was very popular 40 years ago. And as I said, it's still popular. My nagging suspicion, and as we said, it's usually or often outperformed by exponential smoothing. And why are people still interested in ARIMA? My nagging suspicion is that it's because the first forecasters were statisticians and econometricians, and those are a subspecies of mathematicians. And mathematicians like to prove stuff. And when you have an ARIMA process and you can prove stuff about characteristic polynomials, about unit roots, about complex roots outside the unit disk, and so on. You can prove all kinds of things, and mathematicians thrive on proofs. And so they probably found this lovely technique, this lovely model that just allowed them to prove so many things. And they may have lost track a little about the fact that, well, yeah, it's all quite correct if your data generating process is ARIMA, but what if it isn't? Then ARIMA could be an approximation, a useful approximation, but so could exponential smoothing or anything else could be a good approximation to that process that actually generated your data. But suddenly, of course, all your theory, all your theorems, all your propositions, they go out the window. And that's a pity because, well, I'm still a mathematician at heart. I understand this need to have proofs, but it won't really tell you whether for a given time series or even a corpus of time series, multiple time series, it will not tell you that ARIMA will necessarily be good. Also, fun little exercise that if I ever did a course in forecasting, that's one thing that I would do in the ARIMA section. I would have people simulate an ARIMA process. So just pick an order, the PDQ of the ARIMA PDQ. Just pick an order, pick a couple of parameters, make sure that it's nice and stationary and invertible, and just simulate it out for a couple hundred observations. Then take those observations and apply Auto ARIMA to it and see whether Auto ARIMA even recovers the original model form. And if it does it recover the original parameters? And it's surprising how hard it is for Auto ARIMA to recover the actual functional form, the actual model that you fed in. And that kind of tells you a lot about the possible optimality of ARIMA or not.
Just a tangential question. Do you think the number of iterations that we do for Auto ARIMA should be same as the ARIMA model that we fit, so as to give it a really fair chance for it to recover the parameters?
Another interesting question. I don't know whether there's any research done on this grid search that's in Auto ARIMA.
Yeah.
You can give the Auto ARIMA implementations, you can tell it to do an exhaustive search. Then it takes a very, very, very long time. Of course, one possibility would be to do multiple starts. And you might want to bound the parameter space. So typical implementations do not go with the AR component, do not go beyond 5. And for the MA component, I have never seen why you should go beyond that. It's typically doesn't help. It's a good question. And I would say I don't think there is an overall answer, because so much in forecasting, that's another thing that we might come to, so much in forecasting is highly specific to the situation that you're in. So ARIMA, as I said, often enough is not an interesting contender in the first place. And so it doesn't really make sense to think about it too much.
Yeah, when you talk to experts, all these questions comes to mind. And yeah, thanks for your insights. I'm really fascinated by autoregression. And as you can see, our slogan is also decoding the past, encoding the future. I believe if you want to encode the future, studying the past is really important. And I think autoregression in some way encapsulates that. Even LLMs, as you see that, they are autoregressive by nature. Is there some inherent quality that makes it so vital? Is there some kind of memory encoding happening here?
A good question. The relationship between autoregression and memory encoding. Well, a good friend of mine, Skanda Hanachi, has this lovely T-shirt that says LLMs are just ARIMA on text tokens. So it's a very nice T-shirt. Like seeing that on him. And so yeah, to a degree, it's all one thing. And memory encoding, yeah, you could see that as autoregression. Absolutely, definitely. Some people might have strong opinions on that. I don't. I'm absolutely fine seeing it that way. One thing that I have, where I have a bit of an issue with ARIMA or autoregression as such, is we're modeling tomorrow's sales as a function of today's sales and yesterday's sales and so on and so forth. Does that really make sense? As I said, I do retail forecasting. So you could say that today's, or if you're in the middle of summer, your sales of ice cream are likely going to be higher than average. And there might be a high autoregression. If sales are high on July 1st, Northern Hemisphere, then they'll likely be high on July 2nd, July 3rd, and so on and so forth. And you could see that as an autoregression. But of course, sales are not high on July 3rd because they were high on July 2nd and July 1st. Sales are high because it's summer. So one common cause for high sales on July 1st, 2nd, and 3rd. There is no causality. We're on the Causal Forecast podcast here. Not forecast, we're on the podcast here, sorry.
Yeah.
Okay, so we're in a causal situation here. I'm not very good at causality, but in this particular case, you have one cause, which is it's summer, that leads to high sales on July 1st, 2nd, and 3rd. We can absolutely model that as an autoregression and forecast out based on the sales in the beginning of July, absolutely. But I think it would be more enlightening to just say, okay, sales are all high because of a common reason, not because of an autoregression in here. So there's this tension relationship between autoregression can yield good forecasts, but they're not uncovering relationships, causal relationships. So we're having something that gives us a good forecast, but is not very explanatory. just read another lovely paper by Del Giudice, 2025, about this tension between explanation and prediction. And we're back into Leo Breiman's 2001 paper about two cultures, explanation and prediction. And forecasters typically don't care very much about explanations. But this is again my earlier start in the inferential framework and the explanation framework. So my wife's work, the psychologists, they're all about explanation and absolutely not at all about prediction. And the forecasters are mainly about predictions, and explanations are only interesting to the degree that they help us improve the forecasts. And I think the sweet spot is somewhere in between. The forecasters really need to think a little more about explanations and why is the time series the way it is. And that's very important in my retail business, because I invariably find most important thing is understanding the business of a particular retailer, because, for instance, promotions can be so different and have so different impacts, so that it's hugely important to understand the promotional landscape, much more important than using the most complex model afterwards. So you need to get the data right. And conversely, when I'm talking to medical, psychological, and so on statisticians, or the psychologists and so on, they explain a lot, but at some point in time, I'd really like to take some of the data and see can I predict whether somebody will, whatever, suffer from PTSD or not, based on the features that they find are explanatory, as in they're statistically significant. So they always publish about everything is statistically significant. I always wonder, does this feature that they just found, does that improve my prediction for somebody? Because my nagging suspicion is that very often all these features might be significant, but they might not improve our prediction for somebody. And then, as a forecaster, I always have to say, how is that useful to say it's explanatory, but it doesn't help me predict anymore? But that's really kind of a non-forecasting thing to think about.
Yeah, very interesting. We work with a lot of retail, companies out there, FMCG, CPG. I'm pretty sure you must have heard about market mix modeling. Have you?
Honestly, I think I have, but I should probably know more about it.
Yeah, I mean, it kind of blends in or brings, the best of both worlds, the time series forecasting and the regression aspect. It kinds of, lends in the explainability. So in market mix modeling, the question that we're asking is, yes, we have observed the sales, but what led to the sales? I think you talked about promotions a little bit. How much did promotions lead to sales? How much did TV ads lead to sales? Or let's say TikTok ads, Facebook ads. So it's a very beautiful amalgamation of time series and regression, I would say, MMM. But yeah, that could be a topic for another day. Coming back to seasonality, right? What is seasonality, and does ARIMA handle it well, or should we go towards something like SARIMA?
Seasonality is, again, there is no hard and fast definition of that. It's essentially, it's recurring patterns with a cyclicity or cycle length that is reasonably fixed. So the simplest thing that everybody will think about is ice cream sales higher in summer than in winter. So the seasonality, the cycle, is the year. It's a month of year, week of year, day of year pattern. But there is also other kinds of seasonality. And in retail, you typically see higher sales on Saturday, at least in Europe, Friday and Saturday, and then the rest of the week, because that's when people do their big weekly shopping. So you have an intra-weekly seasonality, typically lower sales Monday to Thursday, higher sales on Friday and Saturday. It's seasonality. It repeats. Few people call it seasonality, but it's the exact same effect. If you're looking at electric power consumption, you have, and those are typically measured in 15-minute increments, for instance, and have a huge seasonality within the day, because at night, fewer people will consume electricity, and there is a lot higher consumption during the day, especially around noon, when people will cook their food and turn on their stoves and the fridge will start running. So you have an intraday seasonality. And the fun starts when it all comes together. So electricity consumption, again, you have time of day seasonality, but the time of day seasonality in electricity consumption, of course, varies by day of week, because during the week, Monday through Friday, people are at work. They are at home. 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 They are at h Saturday, Sunday, people are at home or on holidays, and then the patterns are completely different. And same, a dear friend of mine, Bahman Rosami Tabar, does forecasting for the UK National Health Service, and he has lovely time series about ambulance demand. And ambulance demand, again, has patterns. You typically have hourly data here, and you have a peak on Friday night and Saturday night, because that's when people go out drinking and starting to have fights or falling downstairs drunk. And so you have lots of ambulances going on Friday and Saturday evening, but at the same point in time, not during the rest of the week, not on Monday, Tuesday, Thursday, Sunday. So you have seasonality that is overlaying each other, and I like to call that multiple seasonalities. Finally, you have seasonalities. You have patterns that are complex, that don't recur in fixed time periods, in fixed cyclicalities. For instance, anything that has to do with a lunar calendar, like Christian Easter, that moves around in the normal calendar year, all the Islamic, all the Jewish holidays and so on, they're all depending on the moon calendar. And since the moon, unfortunately, does not completely align with our regular calendar, that all that moves around. And that gives you patterns in certain topics, products, and so on that you need to forecast, and they're a bit harder to capture than the regular patterns. Okay. ARIMA as such doesn't do any seasonality at all, because it just looks back a couple of time periods. And of course, you could say, just use an AR that looks back far enough so it captures the same period a year back or something. That's typically heavily over-parameterized. So what we do in ARIMA is typically we not only do the integration, the differencing from one time period to the next, but we also do a seasonal differencing. So if you have monthly data, you take the differences between this month and the month 1 year back. So a differencing of an order of 12. And then we essentially model not the increment time over time, but month last year over month this year, and the same for the next month, and so on and so forth. And that's essentially how ARIMA, seasonal ARIMA treats seasonal data. And then you get these monstrous things where you have a SARIMA model that's parameterized described not by 3 components, the AR, I, and MA component, but also the 3 corresponding components for the seasonal dynamics in here. And so we have 6 numbers that describe your SARIMA model. And even then, when you have multiple seasonalities, as I was saying, these patterns that overlay each other, it's ARIMA and SARIMA starts struggling heavily, and essentially it doesn't work anymore. And that's when you start putting in harmonics and splines and everything. And pretty soon you're in a situation where you're actually running a regression in the widest possible sense. Could be an OLS regression. It could be anything that just takes models data based on these harmonics, and then you apply ARIMA to the residuals, because there might still be some autoregressive behavior in the residuals from your regression. So you mix and match models from time series analysis and from straightforward statistics, machine learning, and so on. Exponential smoothing can be made to work with multiple seasonalities. You then would introduce additional components, one for the day of year component and one of the day of week component, and you'd need to update them all, but it becomes unstable at some point in time. We used to do that 20 years ago in the company that I worked for, and it was horrendous. We're so glad these times are over. So yeah, seasonality is an interesting topic, and there's typically in modern technologies, if you run a transformer that will take care of seasonalities by itself with its attention mechanism, recurring neural networks will also, you need to tell them, okay, my seasonality is probably a seasonal factor of 7 day of week and one seasonal factor of 365 day of year, and then it will do its thing and model all that. And there's also straightforward approaches like multiple STL, MSTL approaches, where you also have additional components for these multiple seasonalities and so on and so forth. It gets interesting and complicated.
Regardless of the methodology or tool, I mean, we at Aryma Labs for market mix modeling advocate our clients that, you need to have at least 2 to 3 years of data so as to, best capture the seasonality aspect. Do you think in retail domain also that applies? Would you advocate for more time period so that the overall forecasting is accurate?
Well, more is always better because you can always throw away data. And that's always what I ask customers when they ask me, how much data do you need? And I say, give me everything. I'll throw everything away that I can't use. More is usually better. The problem is sometimes you don't have you don't have more data because it's a newly introduced product. You don't have 2 years of history because it's only been introduced a month ago. You still need to do a forecast and, oh, look, Christmas is coming up. How is this product going to perform over Christmas? Well, I just introduced it in July of this year. It's never seen Christmas. And that's where you need to start doing cross-learning or Bayesian priors using sales of other products around Christmas to inform the forecast. And sometimes you need to forecast, and then you're going beyond time series. Sometimes you need to forecast products you've never seen before, cold start. Especially important for fashion, of course, where you get new fashion assortments every couple of months or even couple of weeks in fast fashion. And you, of course, need to have forecasts for how much am I going to sell of this particular shirt. So I know how much to order in China or whatever it's actually manufactured. And you need to do that way before the first sale happens because the entire supply chain has to have some kind of runtime, of runway to do that. And you forecast suddenly without any data at all for this particular product. And again, you use analogies. And conversely, of course, sometimes having too much data or having a lot of data can be too much because dynamics change. In retail, you get new product introductions. So even if you have one product that's been selling for 5 years, perhaps in the middle of that, a substitute product was introduced or was taken out of the market, and that may have impacted the product that you're forecasting for. Or, well, it's 2025 right now. I don't know when people will be watching that, but 5 years ago, there was this pandemic. And so any data that's more than 5 years old, you need to think about, okay, can I actually use the very beginning? Can I use what I saw in 2025? I still have this lovely picture of empty toilet paper shelves in my local supermarket during the COVID pandemic, because at least here in Germany, there was a run on toilet paper and there was no toilet paper to be had. So we had 0 sales. And the question is, okay, can we actually use these 0 sales, these zeros in our time series? Can we learn anything from that? And I would say, no, probably not. Just cut it out and start the history of the time series sometime after COVID. And for other things, things might be different and you might be able to learn a lot even from the COVID data. And so forecasting, I like to say, is not a science. Forecasting is an art. It's a craft. It's things work and other things work less well. And it all very much depends on what you're painting, what you're actually do. Techniques that will help you paint a landscape are quite different than if you want to paint a picture of a person or a piece of architecture. And that's where I see forecasting here.
Yeah, great answer. Just building upon seasonality, right? I've seen a lot of people use one-hot encoding. I think it's also called as dummy variable encoding. Perhaps you must have heard about it. That is one way to handle seasonality. Of course, you're right that ARIMA does not implicitly handle seasonality, and hence people resort to one-hot encoding and all that. In my field of market mix modeling, we were using one-hot encoding, or most of the vendors still do. But we, devised a new mechanism to handle seasonality, and we started using something known as radial basis function, which is along the lines of, the sine and the cosine wave. Why do you think this would be better than, just a dummy variable encoding?
Very much depends on the granularity, on the temporal granularity that your data is on. So assume you have daily data, right? So you have total sales or whatever demand consumption on per day. And you want to model date of year seasonality. People might put in dummies for the month. So there's one dummy for January, one for February, and so on and so forth. I would not consider that good practice. Why? What does that mean? That gives you, once you look at the forecast or even the in-sample fit, that gives you a seasonal component that is flat in January, then jumps on the 1st of February down here or somewhere else, and then jumps again for March. So in my opinion, neither makes sense to say it's going to be flat. The seasonal component will be flat on January. That doesn't make sense. And it doesn't make sense to say it's going to jump abruptly on the 1st of February. And that's exactly what you get in dummy encoding. daily data with month of year dummies. And of course, the same if you have hourly data and do daily encoding and so on and so forth. And so I would not do that. I would always use some kind of transformation of the day of year, and radial basis functions are a wonderful example of that, or sines and cosines, or other kinds of splines. So there's so many different things. I actually have, we're going to put a link to one cross-validated thread on that into the description. And it, again, it's an art. It all depends. So if you have a situation where you have retail sales, for instance, if you're a supermarket, then it might certainly make sense to have dummies for the day of week, to say Monday, Tuesday, and so on, because the day of weeks actually do happen differently. And since few people go shopping at night, we typically don't really care about what's happening at night, these jumps between the days make more sense. And Friday and the weekend is qualitatively different from the day of weekend. There actually is a jump in customer behavior between Sunday and Monday. And so here it makes sense to have dummies. And in other cases too, if you have regulatory changes that might give you a structural break where things actually jump from one day to the next, by all means include a dummy there. Even then, it doesn't always make sense because people anticipate regulatory changes and they already change their behavior way before the change happens. But yeah, so dummies can make sense if used sparingly. I think they're overused, and I still see papers where people will use dummies, and it always makes me a little sad.
Yeah, absolutely agree. You're right that, dummy variable encoding introduces a shock. And in our research paper, I'll be happy to share our research paper with you. We conclusively proved that, using radial basis functions to encode seasonality vastly improves models as compared to, just one hot encoding. And yeah, I would love to, hear your feedback on our research paper. I will share it post this podcast session.
They send that out. It doesn't surprise me in the least.
Yeah. I mean, for an expert like you, it wouldn't. But yeah, for a lot of people in my field, it is definitely eye-opening. I mean, the way I explained it to them is that, if you were doing one hot encoding, it's just kind of like putting a pin on a timeline. But, when it comes to retail and FMCG and etc., seasonality is just not, happening on particular that day. It is perhaps, built, there's a prelude to it and there's an absolute. So perhaps you must place some kind of like a conical shape or a bowl, so as to speak, and that figuratively translates to RBF. You're figuratively placing a cup on top of the timeline rather than a sharp pin. Would you be agreeing to that?
Absolutely. It makes perfect sense. Very good description.
Yeah, thanks. So let's come to your favorite topic, that is the hierarchical forecasting. What is hierarchical forecasting? Is there some inherent natural hierarchy that forecast needs to satisfy?
First off, I wouldn't say it's my favorite topic. It's one topic that I like. My favorite topic is actually forecast error measures, but that's too dry even for forecasters. So, and retail forecasting, and that's something I can explain to people. Hierarchical forecasting. Why is that important? So, what is hierarchical forecasting? Hierarchical forecasting is when you have a corpus of time series, multiple time series that obey some kind of relationship in the sense of summation. So the one perennial example of hierarchical forecasting is Australian tourism. So you have the hierarchy is people arriving for the different Australian states and overall people arriving to Australia. Of course, historically, you sum the people that come to the different states, and the total is exactly the time series of total visitors arriving. Okay, and when you forecast out, you can forecast either each separate state's arrivals or the total of the arrivals. And if you do that separately and then aggregate the forecasts for the separate states, just sum them up, then you'll get a different forecast than if you forecast the total directly. And that makes some people very nervous. And I'm using my words with care here because I'm personally not completely convinced that this some constraint is always so useful. Let's work with it for now. Okay, and there's different ways to deal with this problem if you consider it a problem. One approach is of course doing bottom-up forecasting, just forecast states separately and aggregate them up and call that your forecast for the top. Alternative is just forecast the top and then disaggregate down by some way, by some proportions to the separate states. You can say, okay, do historical proportions, or you can forecast the states separately and then use the forecasts as the proportions for disaggregating the total forecast. And the alternative that's been around for almost 20 years now, going back to work by Hindman and colleagues, is optimal reconciliation, where you say, okay, you have the bottom forecast, you have the top forecast, they don't agree in terms of the summation. We can modify them all by doing some actually pretty simple linear algebra and modify them all so that in the end, they are sum consistent. And this is the important part, typically this reconciliation technique will improve all the forecasts. And that's a very powerful idea, extremely powerful idea. It helps for Australian tourism forecasting, also helps in retail forecasting, for instance, as I said, the M5 competition. Because why do we care about forecasts on different hierarchy levels? Well, forecasts are never an end by themselves, right? So having a nice forecast that will give you a nice publication that might improve your academic career. But in the rest of the world, we're not just forecasting to have nice time series plots to look at. We're using forecasts to make business decisions or any kind of decision. For instance, retail, as I said, what I know most about, you need forecasts on the SKU, stock keeping unit, times store, times day level to replenish the store. But you also need a forecast for how much will I be selling in a particular store altogether to understand, do I need 2 or 3 people at the cash desk? Well, how do I plan my workforce? I need a forecast for sales of SKUs across all stores when I want to replenish the central distribution center. So there's different aggregates that we need forecasts for. And you can do all that in principle with these hierarchical forecasting approaches. And you can even, so we're aggregating across the product dimension, the location dimension, and it can even aggregate across the time dimension. Because, for instance, total weekly sales are just the sum of daily sales. So you have 7 daily sales, you sum them up, you get weekly sales. And you can apply again the same hierarchical reconciliation technique to forecast separate daily sales and forecast total weekly sales, then reconcile them using this technique, and you typically get better forecasts across the line, across the board. And so it's an extremely powerful technique. Other ways you can do that, well, we're forecasting cars and the components of cars. And so suppose you have a car with 4 wheels. Those cars have 4 wheels. And so the forecast of wheels needs to be 1/4 the forecast of cars. And so it's again a hierarchical situation where the sum of the wheel forecasts need to be just 4 times the sum of the whole car forecast. You can just put that into a summation matrix where you suddenly don't have 1s and 0s, but you have a 4 in there somewhere. And you can still apply the exact same technique. You can do that with bills of materials, with recipe ingredients, with all kinds of things. So it's an extremely powerful way of thinking at things and improves matters everywhere. There are 2 caveats. The one caveat is that the standard technique of doing that, hierarchical reconciliation, only works with rather small hierarchies. So it works for the Australian tourism data where you have just, I don't know, 7, 10 states, something like that. I'm sorry, I know Australian friends will hate me for that. It works for the 20 ingredients in a recipe and so on. But when you come to retail forecasts, we have thousands of time series, thousands of SKUs, multiple different brands or categories, many stores. The matrices just get so huge that you need sparse matrix algebra. And even then it's a struggle to really make this work numerically. And I really need to talk to a numerical matrix algebraist at some point in time to understand whether we can do that in a smart way. And it's telling that in the M5 competition, as I said, 3,000 time series, 10 stores, as far as I know, nobody used this hierarchical reconciliation technique, even though it was essentially a prima facie showcase for this. It's probably just because the hierarchy was too large. That's the one problem. The other problem is that often enough, we don't need this expectation forecast. How much do we expect to sell? How much demand do we expect to see? But what we need may be a quantile forecast, because we may need to set safety amounts or reserve capacity. If you're forecasting for a call center, you may want to have enough product and enough people on hand to not just handle expected demand, but also to handle spikes. So there's always a variability in here. So we need a quantile forecast. We need a number so we can say, okay, in 90% of cases, the actual observation will come in below that. Also necessary in all kinds of supply chain applications. And of course, quantiles are not additive. You cannot just say, okay, I need a quantile forecast for each product in each store. We sum the quantile forecasts and use that as a quantile forecast in the distribution center. Doesn't make sense because in the distribution center, these variations in the store, they cancel out to a degree. So you need less. The safety amount in the distribution center is much less than that you need than the sum of the safety amounts in the stores. And then this entire hierarchical consolidation technique doesn't work, at least out of the box. And you need probabilistic reconciliation. There's also some work done on that. But of course, that gets even more complicated, even harder to explain, and even harder numerically to work on, especially for large realistic applications. So again, it's something to keep in the back of your head, especially if you have a small hierarchy to forecast for. That's where I always recommend to look at hierarchical reconciliation, because it always helps, or almost always helps in my experience. But once you have a larger one, it's probably not going to do much for you unless you can cut this large hierarchy down into smaller sub-hierarchies.
That was a very insightful answer, Dr. Stephan. I think you can take a sip of water if you want to. That was a really long answer.
I'm sorry, as I said, you may need to interrupt me at some point in time.
No problem. I love, very thoughtful explanations. It really helps. This is another interesting question. This is regarding the granularity, right? If one has data at a granular level, let's say seconds, minutes, hours, days, and months, and even year, does time series forecasting behave well as we aggregate more data? Or do you think, is it unwise to model at a level, let's say seconds or minutes?
Very much depends on the use case. So typically you need, as I said, forecasts are never an end in itself. You need to forecast for a subsequent decision. And this subsequent decision should really be a major driver for the granularity on which you're working. So, as I said, if you're forecasting total sales for a product that you will need to source from China, then you're probably not interested in how much am I going to sell per hour per store. Yeah. Then you're interested in total sales across the life cycle. But later on, when you do replenishment, when the product is already in your distribution center, you need to replenish the stores, then you need to forecast on daily granularity, because you may have one delivery per day, or even 3 days granularity, something like that. So the final output of the forecast should be governed by what you're going to do with the forecast. That, of course, doesn't mean, we just talked about this hierarchical aggregation, consolidation across the time dimension. So you can certainly model and forecast on more fine granular levels and then aggregate up. And one simple example for that is you have a promotion in a store, and the promotion runs for a week and it ends on Wednesday, whatever. Wednesday is the last day of the promotion, but your deliveries to the store come in on Tuesday evening, and the next comes in on Friday evening. So your replenishment, the period that you need to replenish for, that covers a Wednesday that is in the promotional period, and then Tuesdays after the promotional period. And then it makes perfect sense to say, okay, these 3 days are so different that it probably doesn't make a lot of sense to model them as one batch of 3 days. And you want to really model and forecast Wednesday and Thursday and Friday separately, and then aggregate up. And so it always depends. And if you're call center forecasting, if you're forecasting for electric power, you always work on 15-minute increments, because that's the bucket on which you deal with electricity production, purchasing, consumption. That's the granularity on which you can buy electricity or sell electricity on the spot markets, on the futures markets. That's 15-minute increments or hourly increments. Nobody cares about, well, I'm not going to say nobody cares about second-to-second power consumption. That The engineers that do the transformers, they certainly care about that. But those people that do actual forecasting in terms of pricing, electricity price forecasts, they typically deal and work on this kind of granularity. So it all should be driven by the use case, and you should nevertheless always be willing to look beyond that and see whether other granularities can help you.
Mm-hmm. Understood. Let's talk about time series forecasting validations. Why is it said that k-fold validation is a bad idea for time series? In fact, we do also advocate to our clients for MMM that, hey, don't do k-fold validation. You've got to respect, temporality.
Yeah, exactly. I just said it. It's because of temporality. If we do k-fold cross-validation, for instance, I would just pick out every kth observation at random and then fit a model to everything else and forecast or predict these holdout periods and then compare them to the actuals using our metric of choice. But then, of course, what we did is typically we learned from the future. We took a time period, today's time period, and 1 week ago was perhaps in the holdout period. And then it simulates knowing the future, and that doesn't really make sense in a lot of cases. For instance, we often use weather in forecasting as a predictor, and doing that pretends you know the future weather, and you rarely do, right? So we have weather forecasts. So what you should really be doing in anything where this time dimension is important. We talked about at the very beginning that time dimension is often important and sometimes unimportant. But if it's important, then you should really always use this holdout period at the end and just take out the last 20%, fit your model on the first 80%, then forecast out into the 20% and then assess there. And there's different approaches of doing that. You can just take one holdout period. If you have enough data, you can do rolling forecasts, rolling holdouts and forecasts, overlapping or non-overlapping. If you do overlapping, then you have more data, but it's all correlated. So there's arguments for and against everything.
Yeah. Understood. We know about predictive intervals and confidence interval, but in the recent years, there has also been talks about conformal predictions. I'm sure you must have seen, the lot of LinkedIn fights going on about conformal predictions, right? In my personal opinion, I think conformal predictions don't add much value as compared to, let's say, confidence intervals or predictive intervals. What is your take on conformal predictions?
So let's first start by keeping the terms apart. So confidence intervals and prediction intervals, those are two very different things. Yes. And people like to mix them up. So let's invest a few words in taking them apart. So a confidence interval, that's actually an algorithm for giving you an interval for an unobserved parameter of a distribution or something, with the property that if you rerun your experiment many times and each time calculate a confidence interval, so each time you'll get a different one, then 95% or whatever of your intervals contain the true value. That's the idea, and that's the definition of a confidence interval. Always pertains to a non-observable parameter. Prediction interval, in contrast, that's an interval typically in a time series context, in a forecasting context, where you can say, okay, in 95% of cases, the observation that I'm forecasting will fall within this interval. So you actually observe things. You can say this was a good prediction interval, that was a bad prediction interval, because this one only had 50% coverage and I wanted 95 and I claimed 95. And I can say just, it's bad. Can tell that. For a confidence interval, very hard to say. And the two get conflated sometimes because, of course, you can have a confidence interval for the mean, for the future mean of a time series, but you cannot observe the mean, the expectation. You only observe a particular observation, and that typically goes quite a ways beyond that mean, up or down. And so prediction intervals are always wider than confidence intervals for some parameter. And they get confused all the time. Some people talk about uncertainty intervals, where I always have to ask, what are you talking about? All right. Okay. Talk about conformal prediction. And conformal prediction started out in the classification literature, really, 30 years ago by Wolf, Gammelman, and so on and so forth. And the idea was, which I think makes perfect sense, is, okay, when we're classifying our images, with in terms of animals, cats, dogs, and so on, we shouldn't just be saying, okay, this is a cat. We shouldn't also either be saying this is a cat with a confidence of 55%. We should be able to say, okay, we should be able to pre-specify a confidence level and say 9%. Give me a number of animals such that you're 90% confident that the actual animal will be among these animals. So we might say for a given image, okay, this is either a cat or a dog or an eagle or something like that. So a full set of possibilities. And I think that makes perfect sense. And conformal prediction was a way of taking in sample or holdout actually predictions and seeing how good they were, and to post-process them and to give us this kind of confidence set, right, for the prediction, predictive sets, confidence sets. Okay, that was classification. At some point, the conformal inference people started looking to time series forecasting or more general predictive numerical predictions, regressions in machine learning speak, and they applied the same methodology there. And that turned, of course, into prediction intervals. And so, and it's a reasonably elegant technique. And there are some people, especially on LinkedIn, not so much outside LinkedIn. There are some people out there that are very vocal about how good they think conformal prediction is. Okay, a couple of things to say to that. So first thing that I observe is that prediction intervals are really nothing new in the forecasting literature. And people have been doing prediction intervals, so not just saying, I forecast 5, but with 90% confidence, I forecast something between 3 and 8. Prediction interval. They've been doing that for a long time. But what I see nowadays is that people talk about conformal prediction as if it were prediction intervals. They want to say, I want conformal prediction of this level for this time series. And I say, okay, can I also give you a prediction interval that's not based on this particular technique, on this particular methodology? They look at me like, what's he talking about? And then I explain to them, look, there's various ways of calculating prediction intervals. You can do it via conformal prediction. You can do it in other ways too. You can do ARIMA comes with prediction intervals built in. Exponential smoothing, if you use an underlying state space framework, does it as well. And actually this much of conformal prediction relies on looking at in-sample residuals and using them. And the simplest way of doing conformal prediction just says, okay, essentially just resamples in-sample residuals and projects them out. And that's not rocket science. That's something I'm sure that people have been doing that in time series forecasting before conformal prediction came around, but it was never worth a name by itself because it's just so immediate. And one of the other things that I have an issue about in conformal prediction is that lots of people harp on the guarantees, because you do the math and conformal prediction gives you guarantees. It will give you a prediction interval that will contain 90% of future observations, or 95 or whatever you put in. And people tout that as a main advantage of conformal prediction. I always say, well, good to read the fine print here, because this guarantee always comes with a lot of assumptions. In the original case, it was exchangeability of observations, which of course doesn't hold at all in time series context. That's what we've been talking about for an hour and a half now. And more recent ways of saving these guarantees in the case of non-exchangeability is, well, if we at least know how the distributions will evolve, then we can still recover these guarantees. And I always say, well, if we know things, then of course we're always in a better position than if we don't know, but in practice we don't know it, right? And then I go back to my retail forecasting situation and say, okay, look, here's a time series of a product, and that will have its first promotion starting tomorrow. Give me a 90% prediction interval for sales during this promotion that starts tomorrow, and give me a guarantee that you will hit that with 90% confidence. And that's when people usually don't get an answer anymore, because that is just not covered by the preconditions, or either it's not covered by the preconditions, or if you go through the machinery, then you get prediction intervals that are that still cover everything with at least 90% confidence, but are so wide that they're completely useless for subsequent decision making. And so, yeah, I would say conformal prediction is a good tool, but it's a little overhyped.
Yeah, I agree. Talking about other metrics, right? For example, MASE and RMSE. Some people say that they are considered inadequate. Of course, the general public, understands only MAPE, at least in my field of market mix modeling. So we have to go with it, even though I can supply with them even with more robust metrics. Why do you think that is the case? Why do you think MAPE or MASE or RMSE are inadequate? Are there better alternatives?
Actually, I have a couple of papers on that, which we'll
Okay.
link in the description later on. And this is one of the things where I might part ways with other forecasters because I have very strong opinions on error measures, and it's a bit of a hobby horse for me. Problem is, so MAPE, mean absolute percentage error. It's something that you can give to a manager who doesn't do forecasting. They understand what the percentage is, they understand what the mean percentage error is, and that's fine. The problem is, and it also works well on all the time series that you see in tutorials or textbooks and so on, because they're typically have very high signal, like the airline data set. You actually see the trend, you see the seasonality, and it's very easy to forecast, and you can do MAPE, and it's not misleading, and it's all very good. And that's fine. People learn from that, and then they apply their knowledge to other time series that are much messier. And especially when you come to low volume time series with a high coefficient of variation. So the standard deviation of the time series is high compared to the mean. And then you suddenly find interesting effects, especially of the MAPE. So if your time series actually contains zeros, for instance, if you have intermittent demand, you sell a product and in some time buckets it simply didn't sell anything, then your MAPE explodes because you're just trying to divide by zero because you have an error and try to express that as a percentage of the true zero sales. You're dividing by zero. It's undefined. People are unhappy. Okay, so you do some kind of change to that. But even if you don't have zeros, I like to say you just take a standard six-sided die and roll that and forecast that. Okay, so you get 1 to 6, all with equal probability. So the expectation is 3.5, and that would probably be the best forecast. But if you look at the MAPE, I actually can't put together what the optimal forecast is. But if you want to minimize the MAPE, if your bonus is tied to getting a low MAPE on this particular time series, then you're incentivized not to forecast 3.5. You're incentivized to forecast something like 4, I think. Why? If you forecast a 2, for instance, then your error below is bounded by 50%. Because you can not go below 1 in your rolling of the dice, and 1 is a 50% error. But if you just forecast 2 and you roll a 6, then you have an error of 4, and that's 200%. So under forecasting is penalized more strongly than over forecasting, and that incentivizes you to give a higher forecast than the expectation. And so if you really want the expectation of your time series to be forecasted, then using the MAPE as a quality measure could send the wrong signal and incentivize you to give a biased forecast. And I know of people who will take the forecast and know that they're being measured by MAPE, and they just change the forecast ex post. So I have a forecast that their methodology, their software gives them and says, this is an expectation forecast. And they know, well, I'm being measured by MAPE. I'm going to change my forecast. And the same happens to the MASE, which is the mean absolute scaled error. And that's the scaling of the mean absolute error. And that actually elicits or rewards you forecasting the conditional median of your data generating process. And again, look at intermittent demands. If half of your time periods don't have any demand, then by definition, the median of the predictive distribution is 0. And so if you want to optimize the MASE or MAE, then you want to output a flat 0 forecast. And there were a couple of years back, there were lots of papers in intermittent demand forecasting, and they all found that the flat 0 forecast was best and better than the method they were proposing. And they had to, again, tie themselves into pretzels to explain why their proposed method was still better than the flat 0 forecast, even if the flat 0 forecast looked best. It looked best because people were using the mean absolute error, and that simply doesn't incentivize you to give an unbiased expectation forecast. And actually, if you look at the entire discussion in the context of quantile forecasting, quantile forecasts can be assessed using the pinball loss. And that is a completely different thing than RMSE and so on. And of course, everybody understands that you do not want to use a 90%, take a 90% quantile forecast and assess it using the MAPE or the RMSE. Although, aside, I have seen big name management consultants do exactly that. Take a quantile forecast and assess it using the MAPE. Ghastly. Okay. And people understand that the pinball loss is something different than the RMSE. And so you just need to extend that thinking to understanding that RMSE, MAE, MSE, MAPE, they are again all different things. And I personally like to say you should first understand here's my time series, which functional of the time series do I want to forecast? Do I want to forecast a quantile? Do I want to forecast a conditional expectation? Do I forecast something else? Now I know the functional. Now I can say which error measure is the correct one. Should I be using the pinball loss because I want to elicit a quantile forecast? Should I be using the RMSE because I want to elicit the expectation? Now, to be honest, I've never seen a use case where I would want to optimize the MAPE in terms of this being the forecast that gives me the best business decisions later on. The MAPE is good to communicate to non-technical people, but it can be horribly misleading. And I always try to invest in educating people to understand the drawbacks of the MAPE. We're going to have another link in the description later on.
Yeah, and perhaps another podcast to discuss them in much more detail. Yeah.
The problem with that is it fascinates me, but that's probably the mathematician instead of the part-time statisticians in me. But so many people simply their eyes glaze over when I start pontificating about that. So I don't know. I would love for people to understand that and be more enthusiastic about it, but I think it's an uphill battle.
Yeah, I mean, as a partial mathematician, because I have done mathematics only through a bachelor's degree, I certainly appreciate it. But maybe the larger folks out there may not. Moving on to another interesting question. I think this is being picked up from your cross-validated answer. Is there a concept of forecastability? What can be forecasted and what can't be forecasted? I read your answer and found it to be really insightful. If you can just succinctly explain, what is even forecastability?
So you'll need to send me that link because I've written, I don't know how many thousands of answers at cross-validated. I can't recall which one that was. I would say that everything can be forecasted. I mean, you can forecast everything. If you want me to forecast a number of cows that will walk through the door in this meeting room for tomorrow, I can give you a forecast, and probably going to be a very good one. I'll say 0. You can forecast everything. Yeah. I would say that for every time series, there are a couple of very simple forecasts that you can do. You can take the last observation. You can take the historical average if you have a time series. If you want to forecast something that you have no data on, like sales of some new shirt, as I said, you can always give some more or less reasonable number. For instance, looking at analogies, looking at general knowledge about the world. If you want to tell me how many cars are going to rain down from the sky tomorrow, I can give you a forecast that is based on the fact that I have never heard of cars falling from the sky. You can always forecast something. I would say forecastability pertains to the fact, can we improve on that very simple approach? So a standard coin that you flip, you can say 50% heads, 50% tails. And it's very, very, very hard to improve on that. So to all practical purposes, it's not forecastable better than doing this simple, trivial approach. And it's, as I said, it's surprisingly hard to forecast a time series better than using these very simple approaches. And I would count exponential smoothing among these simple approaches. And it's always a question of, do we have extraneous information about that? As I said, I know most about retail forecasting. If I know that there is a promotion coming up tomorrow, then I will probably be able to forecast better than if I didn't know that. Or if that a particular retailer never ran a promotion. Walmart, for instance, doesn't run a lot of promotions. They pride themselves to be an everyday low price retailer. That's a strategy that makes the supply chain move much easier. And it, of course, means that you cannot leverage promotions for forecasting. And so forecastability is always a bit of it needs to be seen in context, right? Here's the corpus, here's the application that I'm forecasting for. Can I forecast better than very simple benchmarks? If I'm looking at power consumption, electricity in 15-minute increments, well, the simplest thing you can do is just look back 1 week to the same time period 1 week back, or perhaps take an average of this time slot over the past weeks. And that's a very simple forecast. That accounts for the intra-week and intra-day seasonality. It doesn't account for the intra-year seasonality. For that, you'd need to look back multiple years and say, okay, perhaps I just don't want to just look at this one slot in this year, but also the slots 1 week before, 1 week after, so you can start getting fancy about that. And if you can improve on that, then I would call that forecastable. And if you can't, then for all intents and purposes, the trivial approach is the simplest and works best, and the series is not forecastable beyond that. And of course, there's this two more things on that. There's one thing that's called this concept of forecast value added that was introduced by Mike Gilliland, back then of SAS, now the chief editor of Foresight, one journal that I need to give a shout out on. And he essentially says, okay, we start with a trivial forecast with a benchmark, and then we can do more complex methods. We can use additional features. We can have consensus meetings. We can have input from whatever sales managers and so on. And so we build like a cascade of forecasts, multiple forecasts for the same reality. And it can for each of these changes in forecast. So simple forecast, forecast plus feature, and complex method, and so on. We always have a different forecast. Store all of these and see which ones are better in terms of RMSE, for instance. And the ones that improve forecasts compared to the previous steps, those add forecast value. And those that make a forecast worse, those destroy forecast value. They're a negative VA, forecast value added. Now, for instance, if you have a sales representative that will always want to have forecast high, so they can get enough budget or something, then their input might be destroying forecast value. And that really ties directly into forecastability. That's the one thing. The other thing is, I've been emphasizing over and over and over again that we're not forecasting just for the fun of it. We're forecasting for a business decision. And the question always is, do business decisions based on better forecasts, are the business decisions better if you're basing them off better forecasts? So you have a forecast that is better, and let's assume we're using a good forecast accuracy measure like RMSE or pinball loss or whatever it is. So forecast A is better than forecast B. Does that mean that the decisions based on these forecasts are better? I like to always give this example. I'm a supermarket. I have 0 stock on hand of a particular product. Forecast method A says 3. Forecast method B says 5. Actual sales are 7. But before the sales happened, I had to replenish based on these forecasts of 3 and 5. But perhaps I can only replenish in pack sizes of 8. So I can buy 8 units or 16 or 24 units. And then if you look at that, and no matter whether you go with a forecast of 3 or forecast of 5, each one will lead me to replenish 1 pack. There are going to be 8 units on the shelf. Both forecasts led to the exact same business decision, same cost, same outcome. And it doesn't matter at all that the forecast of 5 was closer to the actual sales of 7 and was therefore better than the forecast of 3. So the relationship between forecast accuracy and business outcome, that's another thing. It's nice to have better forecasts, but it's a lot nicer to have good business outcome. And the recent M6 forecasting competition, where they looked at stock markets and they actually had to do investment decisions, and they found that the correlation between forecast accuracy and payout in terms of earning money on this simulated stock market or this business game here, there was not a lot of correlation between the two, right? So better forecasts might not necessarily mean better outcomes down the line.
But don't you think stock market movement is more like a Brownian movement and hence can't be predicted or forecasted?
Absolutely. I'm a firm believer in the efficient market hypothesis that all the information is already priced into the stock market. And especially as a retail investor, it's essentially hopeless to try to outguess the market. And so I'm mostly in ETFs.
Yeah. Dr. Stephan, time series forecasting is a very important domain on its own, and we need to talk about it at length. But one of the reasons that I invited you into this podcast is because even causality needs to appreciate temporality, right? I mean, most often than not, we have to take into essence, the time factor, because it could be a confounding factor. I mean, a simplest example that I can give is in middle school, we all have experimented with sprouts growing, right? Like, for example, day one, the sprout is still a seed, but day two, it's slightly coming up. Day three, you see that it's coming up totally, right? And if you arrange it accordingly in time and you have a threshold like day two is the threshold, you will see that just because of the movement in time, the growth of the sprout has happened. But we don't know whether any extraneous factors have influenced them or not. So temporality is very important. Do you think there could be something like a causal forecasting, which could be like acting as a bridge between forecasting and causality?
Extremely interesting question, and I don't know enough about causality and causal modeling to really answer that question. So I have read Pearl's book, of course, but to be honest, in my day-to-day work, so retail forecasting, in case anybody doesn't know by now, we have promotions. And nobody really cares or worries about whether promotions are causal for sales. We just assume that they are, right? We run a promotion, we sell more whatever beer or what have you. And it seems to be rather obvious that there is a causal relationship between the two. Yeah. So that's the one thing. The other thing is that in my line of business, it's very hard to really establish causality by doing some kind of tests, A/B tests, for instance. Could work with TikTok marketing. So just do a marketing to a subset of TikTok users. Could work. It will not work in terms of running a promotion in only half of your stores, because you run a promotion and people will expect this promotion to be happening in all of your stores. And if your customer comes into one of those stores that are in the B arm that do not run the promotion and they have to pay full price when they were led to believe there is a promotion, even if the promotion of the TV ad and the YouTube ad, even if it has small text participating stores only, well, everybody expects all stores to participate, and it can really make people unhappy by doing like an A/B test here. So it's very hard to establish causality here. And same for all the time coefficient time effects that we have in here. You can't just say, okay, well, sales are high because it's Friday and Saturday. Can we devise a causal experiment? Well, very hard to say this Friday, just for our experiment, we can turn this into a Tuesday as an intervention. It just doesn't happen that way. And so I think that causality can make a lot of sense in some time series forecasting domains. And it sometimes plays a role and sometimes it's just very hard to do.
Are ensemble approaches combining different models underrated or overrated in time series forecasting?
Underrated. Far too few people do that. So ensembling is one way that typically improves all kinds of forecasts. And the simplest way is just to run multiple models and just average the forecasts. And that works for the expectation forecast for quantiles. It always works, and it usually improves matters. And typically when I see another paper that compares 10 different methods, you always want to say, well, what happens if you just combine them all? And it's going to be better than everything on its own. There's also some work on pooling forecasts. That's Koventzes and I think Petropoulos, who said, okay, perhaps we don't just want to average everything. We first want to remove the worst performers and just average the 5 best ones, for instance. They call that forecasting pools. That's another approach, but then of course it gets more complicated. I'm a firm believer in simplicity. Simplicity is just run all the forecasts, average everything. It's just going to work so much better.
Agreed. I'm sure you must have built hundreds of time series forecasting models and even consulted for a lot of companies. If you could fix one thing in how companies approach forecasting, what would it be?
I think, I would say the first thing they should do is read our textbooks. Yeah, because that really is a distillation of everything that I've learned over the last 15, 20 years of forecasting. We wrote that one textbook, we're going to link to it later on, essentially to give you a first step into this big black pool of forecasting in which you can drown. And I think understanding the situation is much more important than knowing about the most up-to-date model and being able to juggle like GBM and transformers and so on. Understand where you are, understand what you want to forecast, understand what the main drivers are, clean your data, and by the time you've understood what you're doing and by the time you've cleaned your data, you typically don't have the time to do anything else anymore than just run it, put it into a simple tree or OLS or something like that.
Mhm. Can you please name the book?
The book is Demand Forecasting for Executives and Professionals, and it's actually available online free of charge at dfep.netlify.app. We
Yeah,
want to update it, but we haven't gotten around to it really.
yeah, but I'm pretty sure it will be a great resource for people to read. Uh, I mean, just an extension of the question that I asked just before. What are some great success stories of, forecasting from your career or elsewhere?
Yeah, I was afraid of that question. The problem is that forecasting is a very thankless job, and I don't want to stop anybody from studying forecasting or doing forecasting. But it's the problem is every time you forecast something, reality will humiliate you, right? So
Hmm.
because every forecast is wrong, and the question just is it so wrong that people will start complaining, or will it be a little less wrong and people will be happy enough about it? I have one T-shirt. I have multiple T-shirts that I made myself for forecasting conferences that are all forecasting themed. Great conversation starters. One of my T-shirts is forecasting noun, the art of getting paid for being wrong. Right. So forecasting is a very humiliating experience and career. So yeah. But if you wanted me to choose, then one of my personal favorites or highlights is not so much about forecasting, but about what we did with the forecast later on. We
Hmm.
have a function back to retail forecasting. Always
Sure.
retail. I'm sorry about that. So you're running a promotion in your retail, in your supermarkets, and you typically have a revenue or cost sharing agreement with your vendor. So your vendor gives you the product for a lower purchasing price, and you have to pass on part of that lower purchasing price as a lower sales price to your customer. Okay,
Hmm.
so you're coming up to the end of the promotion. You can now order product from your vendor at the lower promotional price. And you can then, of course, now you have product that you just bought at a lower price. You can sell that at the regular price after the promotion has ended. That's called forward buy or investment buy in the retail community. And of course, the vendors don't like it, but I mean, what are they going to do? They have a
Yeah.
contract. I'm going to sell this to you in this period for this price, and you have to sell it in that different period at a lower price as well. But they can't stop you from doing this forward buy. And we have one such functionality that, of course, relies crucially on the forecasts of the posts promotion demand, because you don't want to stock up so much that it clogs your DC or that it spoils or something.
Hmm.
Well, we have this functionality that allows you to do this forward buy right at the end of the promotion. And there was one customer in our user conferences who rhapsodized about how this functionality that I essentially put together, how that saved them thousands of translated into dollars per store per week. And that was quite an amount of money because in retail they have very slim margins and stuff like that can really make an impact on the bottom line. And that relied crucially on forecasts that were, again, not perfect, but accurate enough, and that immediately turned into business benefit for the company. So once again, it's not the forecast that helps, it's how you use the forecast. Of course, later on, I'm also talking to not exactly those vendors, but I'm also talking to consumer packaged goods manufacturers, and they're at the receiving end of this forward buy, and they, of course, try to minimize that. And I have to account for stuff like that in my forecast for them. So it's a never-ending story. I like my job.
Yeah, great answer. Last question, Stephen, I promise. What resources would you suggest to people looking to get started with time series forecasting?
Okay, short answer, I promise. Actually, we have it cross-validated in the forecasting tag.
Yeah.
There is in the description, there's a link to one thread where we collected a set of curated resources. There's our textbook. There's also other textbooks. Some of them, like the ones by Athanasopoulos et al., are free. Nowadays, of course, people will start getting their information not by reading books, but by watching movies. And there's also a list of YouTube videos put out by the Lancaster Center for Marketing Analytics and Forecasting. They're also very good. Full disclosure, I am affiliated with them. I also did one of those videos, and the links are in there, and we're going to link to that in the description.
This has been great, Dr. Stephan. It was a pleasure to have you. I know we started out this as a podcast, but it eventually turned into a masterclass from you. So thank you for your generous time.
Oh, wonderful. Thank you so much. I hope people will like watching this video. It was great fun talking to you. All right.
Definitely.
Thank you so much. Happy forecasting and looking forward to talking to you again.
Yeah. Thank you, Dr. Stephan. Nice having you.
Goodbye. Thank
Bye.
you.